Okay, today is 4.1 day 3, and I want to do a lot of review today and kind of catch a few things that we haven't finished up. One of which is I haven't taught you cosecant and secant yet, but I'm about to. I want you to start by graphing for me each of these four functions on their own separate little graph. I want you to label them both on the x and the y axis, you know, like 2 pi and pi over 2 and that kind of stuff. And on the y-axis, talking about ones and negative ones usually for parent functions. Then I want you to see if you can write me a more complicated one, this equation right here, y equals, and I'll give you a hint, it's going to be a cosine b of x minus c plus d. But you can figure all those out from the information I told you there. All right, give that one a shot. The four graphs and the one tricky sinusoidal question. And after you've had a chance to work on that for a bit, we'll come back and teach you a couple new functions and a few more things after that. So, sorry about that. We had a little longer than I expected for that, but I'll go quickly here. Sine looks like that, and it goes up to 1 and down to -1, and it ends at 2 pi, and halfway through, of course, would be pi. Raise your hand if you had that one right. Okay, now I want to learn a new function. It's 1 over sine. What is 1 over sine? Nope, not cotangent. Cosecant. Cosecant. Cosecant looks like this. If you're doing 1 over sine, and sine's like right here, then sine is 1. So it's 1 over 1, so it's exactly the same. At that one spot, it's exactly the same. If this is another spot where sine is 0 at that spot, and therefore it's 1 over 0. What about that? Can't do it, and therefore there's an asymptote line that runs right here on cosecant. There's an asymptote that runs right here for the same exact reason, because sine hits 0. Another one here for the same exact reason, and then the easy way to remember it is these are the spots where they share, because 1 over 1 is 1. And it's just a little loop like this, because as sine gets smaller and smaller and smaller, 1 over that gets bigger and bigger and bigger. All right, so there. It's those little red loops. And they stay inside the asymptotes that are formed wherever sine hits 0. That is cosecant. Y equals. Okay. Then I'm going to spread these around a little bit. Cosine. Cosine, of course, is the one that starts with 1 and then goes down. I'm going to make 4 marks on my axis and then say, all right, it starts going down, hits all the way at -1 here, and then all the way back up to 1. And I round it off a little bit at the tops and the bottom. There's cosine. Okay, and it goes from 1 to -1, and its period is 2 pi again. So halfway would be pi. Raise your hand if you had that cosine right. Okay, good. Then what rides in the back of cosine? Its sister function. What is the sister function for cosine? Secant. Secant goes with cosine. You need to keep these straight. Secant is the one that goes with it, and it doesn't turn into it. It's 1 over it. 1 over cosine is secant. So 1 over this means whenever it would hit like right here or right here, whenever cosine is hitting 0, it's 1 over 0. So it can't exist. And so now, to finish it off, I need the loops again. Loop like this. And I'm only doing half of a loop because that way I keep it to just one, what do you call it? One complete cycle. I could trade in and not graph this left one if I wanted, and instead fully graph this one. You get how then I have 1 down and 1 up? All right. But if you wanted to graph it from 0 to 2 pi, it would need to look like that. Now remember, this is just kind of artificial because this will keep cycling over and over and over, and so secant will just keep doing this over and over and over. Okay? So just like cosine keeps going forever to the right, secant also would follow it and ride on its back. All right, so there is your 2 new functions. Now how about tangent and cotangent? Well, tangent's graph looks like this. Asymptote down here, asymptote down here. That's at pi over 2. This is at negative pi over 2. How many of you remembered that? All right, that's important to remember because this has a different period of all the others. It has a period of pi. Cotangent also has a period of pi, but all the other graphs, sine, cosine, cosecant, etc., they all have a period of 2 pi. Just tangent and cotangent have a period of pi. Half a pi this way, half a pi that way. All right, so the final actual graph of tangent then goes like this. And if you go halfway over here, you'll hit exactly at 1. If you go halfway over here, you'll hit exactly at -1. There we go. And it actually makes a lot of sense because this is pi over 4, also known as 45 degrees. And do you know that tangent of 45 degrees is 1? And that makes sense, doesn't it? All right. So that's tangent, and then cotangent. Cotangent's graph would look similar, but it's shifted over because cotangent is cosine over sine. So wherever sine hits, since cotangent is cosine over sine, wherever sine hits 0, which is like here and here and here, it needs asymptotes there. So if I take this original out now and say, where should cotangent be? It'll be inside those asymptote lines. And once again, it's 1 pi for its period. So this is going from 0 to pi. And cotangent goes down the whole time. So cotangent would be like that. And same deal, we're halfway between where it hits the origin and its asymptote. It ends up at -1 here, and it ends up at +1 halfway between here and here. So this is pi over 2, and that's all you'd have to have for labeling. But just so you know, this is pi over 4, and the cotangent of pi over 4 is 1, and the cotangent of 3 pi over 4, which is right there, is -1. All right, that's cotangent and tangent. Adds to your list. Now you got all 6 parent functions. So what could we ask you for on the test? We could say, I want you to do 3 secant of 2 theta minus 7. You'd have to be able to graph that. I'm not going to ask you to do it right this second, but what would be the A term? 3. And it's the, well, it's an amplitude, but when you're talking about cosecant, secant, it rides in the back of cosine. So here's cosine. And if we make our cosine go up to 3 and down to -3, then our secant will follow it. So then, sorry, this, that, and that. The asymptote lines run right down through there, right where cosine hits 0. So that would be our graph of secant, where it's got a 3 here in front. And how about the 2 theta? Well, then we'd have to adjust our numbering. Normally it ends at 2 pi, right? And this 2 here is the B term. I'd like you to figure out for me, what would my new numbering be? What would my new period be? Don't say it, write it. Use the little formula that you know about periods. Periods are equal to this, or you could say B is equal to this. There's 2 formulas you know about that. Mr. AO, what's the formula? Okay, this is a true thing, but you're thinking of a different formula. I'm talking about the formulas for period. Okay, good. And is the period of secant, because it's based on cosine, is it still 2 pi for a period? Yes, it is. So what's our B term here? In this problem, what's B? It's not a hard question. Somebody say the answer. 2. 2 is the B term. There's the 2. That's B. Okay, so that becomes a 2 right here. And do you get that then what's our period? Pi. So do you get how this shouldn't be labeled a 2 pi anymore? Because our period is actually, it's going to finish up by pi. So we should change our 2 pi to pi. How am I really doing that? I'm dividing it by 2. See, if this is multiplied by 2, that gets divided by 2. And then this spot, which was halfway through, was pi. Now we got to change it also. Cut it in half, pi over 2. So pi over 2 and pi would be our new numbering system based on that. And then what's this minus 7 do? Moves the whole thing down 7. So I'd have to take the whole thing, move it down 7. And technically, do we need that in there? No, because that's cosine. We aren't even graphing cosine. We're graphing what? Secant. So this needs to just leave. And I'll put in my label here of 3 and negative 3. And there, that red graph, except everything about the red graph shift down 7. So when this goes down 3, it hits here. Down 6, down 7. That would have to go off the screen way down there. And then this will go down 7. There we go. So something like that. All right. That's about as tough as it could get for graphing. Now how about that problem back here, this one? How many of you feel like you have that one mastered? You've got the right equation for this in the upper right-hand corner. All right, I want you to compare it with the person sitting next to you and see if your equation looks the same as theirs, and if not, talk it over. I want to see a lot of comparing going on. So, let's see if you did it right. You've talked to your partner about it. Hopefully, you guys agreed. There's a little dotted line that should go in here. If you haven't been doing that, you really need to learn how to do that. That's really, really critical because it helps you with 2 things. It helps you know how much is the amplitude, because from that little dotted line up is the amplitude. All right, well, that dotted line would be running right between 2 and 5, which is exactly at 3.5. That dotted line then tells me that my amplitude is from 3.5 to 5 is the height of the wave there, and that's a 1.5. 1.5 cosine of, and next I got to figure out the b. Definitely the hardest part. Okay, so I got to know the formula for that. Period equals 2 pi over b, or b is equal to 2 pi over the period. So how do I know the period? I can look at the graph and say, if it took me this long to get halfway done completing it, it'll double that to finish. So how long did it take? It took from pi over 4 to pi over 2, which is 1/4 of a pi, because 1/4 plus 1/4 makes a half. All right, so 1/4 of a pi doubled is 2/4. 2/4 is 1/2 pi. So its period right now is 1/2 pi. 1 pi over 2, or 1/2 pi. You flip and multiply, and the 2 ends up on top with the other 2. The pi ends up on the bottom, and the pi's cancel, and you got a b equals 4. Raise your hand if you had a 4 for that spot right there. All right, if you didn't, that's an important spot you need to learn how to handle. Otherwise, you're not going to be an A student. All right, on to the next part is x minus, how far did it shift? Well, can you tell that it did have a high spot right at the y-axis there? Okay, so it didn't shift at all. But would you agree, if you wanted to, since we know that the period is pi over 2, the period is pi over 2, do you get, if you wanted to shift the whole thing over pi over 2, it's just like moving a normal one over 2 pi. Do you get how it wouldn't have hurt it at all if you had done that? All right, so if you wanted to, you could say it shifted to the right pi over 2. Notice that's the height of this. It's the maximum of one of your peaks. Now think about it. Every time you hit a new maximum, do you get it's going to be, normally it'd be 2 pi apart. But in this case, it's an extra pi over 2 every time. You're just adding pi over 2. So if you wanted to have this, cool. Notice it's this number. But you didn't have to have that there, because that's, again, like not having shifted it at all, or having shifted it right pi over 2. The x value of your peak. All right, and the last thing is, how far up did it shift? That's another reason this dotted line is really smart to do, because it's up 3.5 plus 3.5. Again, this was optional. I'm just setting you up for the real world problem we're going to do in a minute. So remember that. But how many of you had that with or without the pi over 2? Okay, so that's obviously the hardest part for you because there's only like 8 people that had it right. Any questions? Yes. Why is that pi over 2 optional? Okay, because do you get on the circle, if I get the answer right here, and let's say that I figure out the answer right there, let's do a 30-degree angle so we know what we're talking about, that if it's 30, 60, 90, this is 1, 2, square root of 3, and if I get the sine at that spot, sine of 30 degrees is opposite over hypotenuse is 1/2. Do you get, I can add 2 pi to that because that's what its period is? Do you get if I added 2 pi to the angle right here, I could add 2 pi to it and it wouldn't do a thing? You guess give me the same answer? Same exact thing. Back to this. If I move it to the right, it's not 2 pi because this guy's got a different period. But its period is pi over 2. So if I move it to the right, pi over 2, it's like going all the way around the circle one time and you're back in the exact same spot you were. Sure. Another way to think of it is, if I have this wave, and the wave, the sine wave, goes like this, do you get, if I want to move it from one peak to the other peak, it's going to look exactly the same? It will look exactly the same in the long run. I should have done out more of this graph, but if you go from peak to peak, you're going to get it's going to look exactly the same. It'll be right on top of itself. So if I move it over 2 pi, it's not a problem. All right, so why am I saying all that? Because I'll give you one more of those real world problems, and this one's going to be very similar to the one we just did, except it's going to be more, imagine this situation. You've got a post, and you're watching the seawater on this post, okay? And you get, if you got a wave here hitting your post, if you're watching it from over here, you're sitting on the dock by the bay, watching the tide, blah, blah, blah. Here's you laying out on the dock, looking at your, I guess you're like an alligator. You are looking at that, okay? And as your waves are going past, you're like going, oh, now it's at 6 feet up on the pole. Let's say this is at 6 feet. And now it's higher. Now it's up at 8 feet on the pole. And then the waves keep on moving, and now it's lower, and now it's higher, and now it's lower, and now it's higher. And do you get the idea? Okay, could you have videotaped that, for instance, and then played it back in slow-mo and seen if you had like labeled your post with, you know, with feet on this, like 6 feet, 7 feet, 8 feet, 9 feet, 10 feet, okay? You could have actually videotaped it and then took your data down. All right, let's say that you did that, and you got, at time 1.5 seconds in your video, you had a height of 6. At time 2.5 seconds, you had, then by the way, that was the lowest height was 6. At 2.5 seconds, you had a height of 8. I'd like you to sketch the situation, like sketch your sinusoidal, make that little dotted line that runs down the middle, and figure out the equation for it. And I bet almost everybody is going to do the, which part? Well, I'm just going to say one part. There's one part almost nobody ever gets right. So do your best to consider that a challenge. Not many people are going to get the whole sinusoidal equation right. You can start with cosine. A cosine B x minus c plus d. See if you can figure that out for this situation. Again, a picture's worth 1,000 words. If I were you, I would be making like a XY axis with a wave and a dotted line and labeling your low spot, your high spot. Okay, I'll pause for a second and give that a try. All right, let me give you some help on this. So first thought, I suggested that you sketch it. I'm going to try to do a pretty good sketch here. Because really, I think you guys underestimate how powerful drawing a good picture is. All right, would you agree this thing has heights of 6 and 8 as it's like low spot and high spot, and therefore it's way up here? it's a lot higher than like where it would have been originally, which would have been down here. The little line that runs through the middle of it, like if the lake had gone suddenly completely calm, there's no waves anymore, that line would be halfway between the low spot of 6 and the high spot of 8, which makes that dotted line at 7. Raise your hand if you had a dotted line at 7. Okay, good. Then you should have said the amplitude is 1, so that's just a 1 for the A. How about the B? Well, the B is one of the tougher ones to figure out. We need a formula for that. Period equals 2 pi over B, or B equals 2 pi over the period. Do I know B? Did they tell me B? No, did they tell me the period? Yes, just in kind of a cryptic way. If this is at 1.5 time-wise when it hits the low spot, and when it hits the high spot, it's at 2.5, then do you get 1 second has elapsed between the low and the high spot? Does that complete a complete cycle? No. That's half of a cycle, and therefore 1 doubles to 2. Your period must be 2. Do you get I need to put the period of 2 right there? So what is our B? 2 pi over 2. Cancel the 2's off. Our B is pi. If you didn't get that, I bet you didn't either write out the formula, or you didn't figure out that the period wasn't just 1, it was double that, it was 2. If you knew the period was 2, you could see it's 2 pi over 2, and therefore B is pi. All right, yes?
Do you know whether it's cosine or sine?
We are always going to use cosine. It'll keep your life simple, period. Okay, you actually could do the equation with sine, but it's especially this next part that makes cosine much better. The next part is the shift. How far over should I say it shifted? Do you get, if it took 1 to reach this peak, this direction, that its last peak before that would have been 1 in this direction? Which means our first peak that we would have had before we started recording would have been at 0.5. Do you get that this peak right here would be at time 0.5? That means this axis here needs to be like budged over a bit. This first peak would have been at time 0.5. Do you get why? Because if it's 1 from here to here, then it's going to be 1 from here to here. Okay, so do you get then that this has been shifted a little bit? All right. I would have accepted 0.5 for this shift because that would have been the first peak. Or, think about it, if you add a full period to that, which is 2, it could have been 2.5. Do you remember me saying that the x-coordinate of the peak could just go right there? I'm going to go back to this problem and show you. Do you remember seeing this? And you remember me saying this was the x-coordinate of the peak, could go right there? Yup. That's pretty slick, isn't it? It's pretty easy, isn't it? Now, would I have accepted 0.5? Sure. But 2.5 is the same exact thing because it's moved over 1 period from 0.5. So 0.5 right here or 2.5 right here. The easier one is to just pick the x-coordinate of the peak. All right, and then the last thing is the plus d. How much did it move up? Well, this line is our how much it moved up line. And that is up to 7, and it used to be at 0, so it is a 7. So the final answer is y equals 1 cosine of pi x minus 2.5 plus 7. Now that's actually pretty powerful. Just think about that. You now have an exact equation for a wave that you could find that got on Lake Minnetonka. You could actually say, I see a wave on Lake Minnetonka. I'm going to go over and look at a post. I'm going to videotape it. I'm going to record its low spot, its high spot, how much the difference was between the two. And you could actually write an equation for a wave. It's kind of cool. It would actually work. There are things in the real world that can mess with it, of course. When you have waves that are in with other waves, like on the lake, have you ever been out there? There's a wave and then it merges with another wave that happens to be like coming across the lake in the other direction. And then it like gets really big all of a sudden for a second when the two waves overlap. So There are going to be a lot of complicated situations in the real world, but we can write a basic equation for a wave. All right, now let's look at your homework for tonight. Everybody find this one. Can you unplug, please? Thank you. There we go. I need your full attention. Number 31. This one's just like what you just did, and I want to warn you that what's inside here is the only weird part. Do you get there is no plus or minus in there? Therefore, there is no shift to the right. Okay. Could I have put an x in instead of the t? Of course I could have. It's just a variable. I could pick any variable I want. Most of your equations would have had an x right there. And the only thing, I know this is a problem from the previous assignment. Okay, it's about the butterfly population, and they're just trying to see, could you actually graph this? Sure you could. The weird thing is going to be your b term. Your a term is simple, it's 2. Your d term is simple, it's 3. Why is that the d? You could put it at the end, couldn't you? And say plus 3 at the end instead of plus 3 at the beginning. All right. So then factor out what's on the x. What's on the x? No, be careful. 3 pi over 8 times x. All right, so that's your b term. And if you know the b term is 3 pi over 8, then period is 2 pi over b, and you know b. B is this. So then you have to do this little complicated calculation, and you'll get an answer. It's okay that it's a weird number. That's all right. All right. There was no horizontal shift. Why? Because there was nothing being added or subtracted in there. There wasn't like plus pi over 6 at the end. There was a vertical shift, though, because this plus 3 at the beginning could have been moved to the end, and so that's pretty simple. The vertical shift part's easy. What does this mean? It's a domain. That means you can only do this graph between what and what? Between 0 and 12. I will give you this hint. You do not need to graph it all the way until 12. If you do one period of this graph like we normally do, which of course starts with a normal sine graph, and 1, 2, 3, I should do my little marks like I usually do. My alignment's off right now, so this has been a little bit painful. I'm going to try to just do it quickly. Dang, I missed it. Should be ending right there. Anyway, okay, normal sine graph, except if you do one complete period, you'll be between 0 and 12. 12 would like end like way over here somewhere, so don't worry about, you don't have to keep graphing it all the way until 12. But that's all this would mean, is the graph only works between 0 and 12, and after that it's no longer defined. All right, 32 will be similar. Those are doable. Number 6, also doable. But I want to make you think about this for a second. What's the minimum on a cosine graph? Well, it's the low spot. Couldn't you tell what the low spot's going to be if I told you the amplitude and how far up it's been shifted? Good. Well, this is how far up it's been shifted, and that's the amplitude. So you should be able to figure out what the low spots and the high spots are. All right. So that's doable. This next one is one of those real-world problems I just showed you how to do. I strongly encourage you to practice this one. Yeah, these are assigned, yes. All of these are assigned so far. And this last page, I'm going to change this a little bit. We're going to just cross off 44. You don't need to do that one. And on 45, I would like you to practice one of those new functions I just taught you. We'll do secant first. So this is going to be 3 secant. Just graph 3 secant. So that's going to make you start. Remember, secant's the one as a sister function of cosine. So you're going to start by graphing cosine, and then it rides on the back of cosine, and then you just got to do a little stretch. Try to figure out what that 3 in front means for the renumbering. And then the next one I want you to do is cosecant of 4x. So if you know what cosecant looks like by now, which it rides on the back of sine, then you're going to have to adjust its period because I just gave you a b term of 4. All right. That makes it, all those problems are doable. And that's your new stuff for tonight. Then, tomorrow, Wednesday, we do a little bit of review. And tentatively, your test is on Thursday. It's going to be 4 questions long. No help this time. Same as the last test. Remember the last test was 4 questions long with an R4, except you had help. This time, no help. So be ready. Make sure you study. This is the stuff I'm doing with you right now. It's exactly the kind of stuff you need to know how to do for the test. Yes, sir? You do. You have one more little mini unit before spring break. So, it's just to clarify though, this is the last unit that's on this this quarter's grade. This quarter's grade, this is your last test. Now, a lot of kids worry about their quarter grades. You really shouldn't, because semester grades are all that really matters in the end. Colleges look at your semester grades, not your quarter grades. In fact, but once you're done with the whole semester, the quarter grade disappears. It's like it was never there. You just see the semester grade. Okay, so if your grade isn't where you want it to be, I mean, you shouldn't take it lightly, but it's not, nobody's going to ever see you just missed the A-. Doesn't matter. So all that matters is the semester grade. Okay, so, all right, that's all I have for you for today.